Okay, hello everyone. So today, Stefano Pironio from the University Libre de Bruxelles is joining us. So he's going to tell us about certification of quantum correlation. So we are very pleased to have him here.
Okay, thanks a lot, Cihan, and thanks for the invitation. So I'm going to talk about rooted Bell experiments. So this is a variation on standard Bell experiments. So I will explain what this variation here, but let's just first briefly remind what are standard Bell experiments, right? So we have some source here in the middle that produce two entangled particles. So one particle goes to the left to Alice, one particle goes to the right to Bob. Alice and Bob select some measurements to do. So here labeled X for Alice, Y for Bob, and then they get some outcomes, A and B. And the correlations between Alice and Bob are characterized by the joint probability to get outcomes A and B given that they choose measurement X and Y. And when you do this kind of measurement on entangled particles, so typically you get very strong correlation between Alice and Bob. Strong meaning that they violate Bell inequalities. And as you know, this violation of Bell inequalities proves that this correlation cannot be explained by an underlying fully classical model that would respect locality, meaning that what happens on Alice's side depends only on her measurement and the quantum particle coming to her, but not on the measurement done on Bob's side and the other way around. Okay, and these very strong correlations, they have important implications for the foundations of quantum theory. They were introduced by people thinking about the foundation of quantum theory. But in, let's say, the past 15 years, they also have acquired some spatial status in quantum information theory. And this is due to the fact that when you violate the Bell inequality, you not only certify that the correlation are non-classical, but you can also certify many quantum properties of the underlying systems. For instance, you can maybe prove that the state which has been produced by the source is close to a maximally entangled state of 2 qubits. You can certify that the measurements have some specific form, so maybe they are Z and X Pauli measurements, and etc. And so we can use this self-testing property of Bell inequalities to actually certify also the correct behavior of entire quantum information protocols like randomness generation protocol, quantum key distribution protocol, or even full quantum computation. And the nice thing is that to certify the correct behavior of these protocols, we don't need to trust the device. We can simply rely on the data, on the fact that there is a violation of the Bell inequality. Okay, so now when we use this kind of experiment for protocols like quantum key distribution, we need Alice and Bob to be located very far away from each other, right? We want to establish this Bell violation over large distances. And typically we do this with photons, because photons can travel large distances. But then there is a problem, which is that there will be losses on the channel, right? So if I send a photon in fiber, this photon will be absorbed by the glass making fiber, or will be scattered. Even in free space, it will be scattered by the air molecules. And so actually most of the photon will not make it to the measurement device. So there will be some detection efficiency that will be associated with the measurement device of Alice and Bob. So this detection efficiency is the probability that a photon produced by the source is actually being measured at the end. Okay, so it's the for every run in the experiment is a priority to get a click when you do an experiment. And so we have a detection efficiency, which I call eta. So we have one for Alice, eta A, and one for Bob, eta B. Okay, so now, when we do this experiment, so we sometimes get a proper outcome, sometimes we get a no-click event. We did the measurement, nothing happened, and we cannot analyze the data by simply discarding the no-click events, because that would open a loophole. If we just post-select the experiments on the conclusive outcomes, then this opens a loophole and makes it possible for a classical model to simulate a bad violation. So we need to take into account all events, including no-click, into the analysis. And one possible way to do that is simply when we get a no-click result, we simply assign it one of the possible value of the ideal measurement. Okay, for instance, if our measurement device gives two outcomes, +1 and -1, when we get a no-click, we will say, okay, this is actually a +1 event. Okay, and so this is one way to take into account these losses. And actually, for simple Bell inequalities like the CHSH inequality, this is the optimal way to take into account these no-click events. So if we take the CHSH inequality and we look at the ideal strategy, which if everything is perfect, will give us a value of 2 square root of 2. So now if we take into account these finite detection efficiencies by assigning the no-click events to say +1 on the left and +1 on the right, this will change the CHSH value, and so we get this expression, which depends on our efficiencies, and the result of these photon losses is that this will decrease the CHSH value. And to witness quantum non-locality, we need this value to be higher than 2. And in this plot here, what I represent is the possible value for the detection efficiencies at Alice and Bob's side. And the red region is the red region where this CHSH expression, taking into account detection efficiency, is above 2. So to observe in an experiment a proper violation of CHSH in the presence of losses, we need the efficiencies of Alice and Bob to be in that red region. So you see, basically, we need very high efficiency, around at least 80%. The problem when you do long-distance experiments is that the losses increase with the distance. They increase exponentially in fibers, quadratically in free space. And so even after a few kilometers, you're actually in a parameter space, which is here. So the opposite corner of the region of the parameter space where you can observe a genuine violation, right? So this means that in practice, we cannot certify long-range quantum correlations. And so we cannot also use this non-local correlation for quantum key distribution experiment over large distances. There have been proof of principle demonstration of device-independent QKD, but these are basically tabletop experiments, right? We cannot do that over more than certainly 2-3 kilometers. So this is a huge problem for the application of this non-local correlation in quantum communication experiment. And so 2 years ago, there was a paper by Chaturvedi, Viola, and Pavlovsky, who introduced an idea which they claim could solve this problem of photon losses. And so their idea is what I now call a rooted Bell experiment. Okay, they did not introduce this terminology, but this is how I call their proposal. So what are rooted Bell experiments? So this is exactly like a standard Bell experiment. So we have source, some measurement device for Alice, some measurement device for Bob, which is here in this gray box. But in between the source and Bob, you add a new measurement apparatus, and you had some switch that can route the particle of Bob either to this new measurement apparatus or to the far away original apparatus of Bob. Okay, so we have the possibility to route the particle to two different measurement devices, one which is close to the source and one which is further away from the source. Okay, and this choice is controlled by some classical input z, which can take the value s or l. Okay, so if s is selected, we route the particle to the close device. If z is l, we route the particle to the device which is far away. And this additional measurement device and this additional switch that route the particle, it's untrusted. Okay, so as in a standard Bell scenario, there are black box device whose internal behavior is not assumed to be trusted. And so now, when we do like a routed Bell experiment, again, we know we can we get some correlations, and now these correlations are described by a joint distribution, representing the joint probability to get outcome A and B, given that we did measurement X on Alice, given that we made a choice, Z, for where the quantum particle has to be sent, and then given that we made a choice Y for the measurement to be performed either by one device or the other one. And by repeating this experiment many times, doing random choices of the inputs, collecting the outputs, we can now estimate two types of Bell quantities. So if we do like a CHSH experiment, we can observe a short path CHSH value that involve Alice and the measurement device close to the source, or a long path CHSH value, which involve Alice and the measurement device, which is far away from the source. So we get these two quantities instead of one. Now the idea is that both Alice, the switch, and the short path Bob will be very close to the source. If they're very close to the source, we can, the losses will be very small. Okay, so we can expect to have a very high quality short path CHSH violation, while the other measurement device is far away, so there will be photon losses. Now, if we do like a standard analysis, like in a standard Bell experiment, and we've observed, this long path CHSH value, well, the condition to roll out a classical model is that this CHSH value has to be bigger than 2. Okay, 2 is the classical bound. However, in their paper, so Pawlowski and his collaborator argue that if you actually observe a violation of the short path CHSH value, then this will actually weaken the condition for rolling out classical model in the long path. So specifically, they derive a trade-off between the short path CHSH value and the long path CHSH value, and this trade-off holds for any model where this device is classical. Okay, so if you violate this threshold, it means that the faraway Bob had really to measure a quantum particle, and so you have established some long distance quantum correlation. You are able to certify long distance quantum correlation. So let me explain a little bit more what this trade-off is. So here in this diagram, you see on the x-axis the short path CHSH value, and on the y-axis the long path CHSH value. So the blue line 2 is the classical bound of the usual CHSH inequality. Okay, you need to be above 2 to certify quantumness, let's say. Now, according to the analysis by Pawlowski and his collaborators, if you observe some violation of CHSH in the short path, the classical bond for the long path CHSH value will decrease. Okay, and if the CHSH short path value is say close to the maximum, 2 square root of 2 minus epsilon, then the classical bond for the long path CHSH value will be square root of epsilon. Okay, so well below 2. So it becomes much more easier to witness long distance quantum correlation, given that you have observed short distance quantum correlation. So why is that nice? So again, let's put some finite detection efficiencies. So let's assume, as I said, that Alice and this measurement device on both sides are close to the source. They're close to the source, so the detection efficiency is some eta s, okay? And we assume eta s is actually close to 1. And then we have the other measurement device, which is much further away, characterized by some efficiency eta L, and typically eta L will be small, okay? So again, we can assume that we start from some ideal strategy, that will, if there were no losses, will give a value of 2 square root of 2 for the short path CHSH, 2 square root of 2 for the long path. No, we add the losses, and both the short path and the long path CHSH value will go down. And we can ask when, for what values of these detection efficiencies do we violate this bond that derived? Okay, and this is represented by this red region. Okay, so the dotted black line, this is so above that dotted black line. This is the region where you would conclude that you have ruled out classical model in a standard Bell experiment. But now you see that in this rooted Bell experiment, you increase that region, okay? And if the efficiency close to the source is really close to 1, you can tolerate efficiency for the long path, which are very, very small, and actually tending to 0, okay? And you will still violate this classical bond. Okay, so the message here is that if you're able to do high quality CHSH tests close to the source, and this is something we can do with current technology, okay, we can do tabletop Bell violation experiment with very high efficiencies, then we can significantly extend the range over which quantum correlation can be certified. Okay, so this is the main message, and this was their proposed solution to this photon losses. Okay, by the way, if something is not clear when I talk, don't hesitate to interrupt me.
Can I ask a question? It might help because I'm not really so much familiar with the rooted scenario. So if you have these two paths, should I think of there's some sort of a so what is the mathematical representation of these two different paths? Is it something like a quantum channel being applied to different quantum channels are being applied to the system? Is that how I should think about the different routes?
That's so I'll come back to that, and I'll write down a proper mathematical formulation of this experiment, and yes, that would be something like that. So I'll come to that, but now I'm just stating the claimed results of this analysis by Pawlowski. Okay, but indeed, okay, I'll come to the precise mathematical formulation of the experiment. Okay, so let me just explain a little bit what is the intuition between this trade-off here. So here is the intuition. Okay, so we have two kinds of situation, right? Either the switch selected the short path, or the switch selected the long path. If we look at the subset of runs where the short path was selected, and if we do observe a violation above 2, then we know that the device of Alice and the short path Bob must measure a quantum system, right? So we know that the source is producing quantum particles in some entangled state rho AB. Now, if we look at the long path, and let's say we observe a violation of CHSH which is below 2. Okay, so normally in a standard experiment, if the violation is below 2, we would conclude that it's actually not quantum system are not needed to get that value. We can do this in a purely classical fashion, right? But is it also the case here? So let's see what would happen if we don't have a quantum particle that reach this faraway device. Okay, so let's assume that the output of the device which is far away, let's assume that it's determined by some classical variables lambda. Okay, and then you are going to see how large can this long path HSH value be. So now the picture we have is that we have this source producing some quantum particle that goes on Alice side, some quantum particle that will be measured in the short path, and some classical variable lambda, which determine the outcome of the faraway device. And these three systems, A, B, lambda, they can, of course, be correlated. So we have like a joint quantum state rho A, B, lambda. Okay, so now let's assume that in the short path, we see a perfect CHSH violation, so 2 square root of 2. So if we reach 2 square root of 2, we know that basically, up to local change of basis or local isometries in general, there is a single quantum strategy that can reach 2 square root of 2. And this strategy involves Alice and Bob measuring a maximally entangled 2-qubit state, a 5+ state. Okay, and then we know that then the quantum register A and B cannot be correlated by the monogamy of entanglement, cannot be correlated to the classical variable lambda. It then follows that Alice and the faraway Bob are not correlated at all. And the maximal value of CHSH you can reach is actually 0. So the classical bound 2, you can reach it with classical systems, but you need classically correlated systems. If the two systems on Alice and Bob's side are completely uncorrelated, then the maximal value of CHSH you can reach is not 2 actually, but 0. Okay. And so here we reach that this has to be the case because we have a perfect violation between A and the short path Bob. And so this excludes any correlation with this additional classical variable that describe the behavior of the faraway Bob. Of course, in a real experiment, you don't observe a perfect CHSH violation. You observe some violation above 2. But then, you can basically do some math and conclude that the joint state has to be close to a 5+ state. And so lambda cannot be too much correlated to A. And then if you do things properly, you get this bound. Okay, so this is the intuition. I don't know if you have any questions so far, or if this is more or less clear. Okay, so we read this paper, but in Brussels we are not entirely convinced by actually the arguments, and we actually found that there was a quite simple strategy, purely classical on both sides, and which actually allows you to violate this bound. Okay, and I will explain you what this strategy is. So the strategy is the following. So we assume the source sends a 5+ state, okay, that Alice does sigma z or sigma x measurements, and that the short path Bob does this sigma z plus x or sigma z minus sigma x measurement. Okay, so these are it's the ideal strategy that gives you a value of 2 square root of 2. Okay, so what about the long path? So of course what the source does, or what Alice does, cannot depend on what happened on Bob's side. Okay, so we assume here there is some kind of causality constraint. Okay, so what happens as in a regular experiment, what happens on one side cannot influence what happened on the other side. Okay, so in the long path, it's still the case that Alice is doing some sigma Z or sigma X measurement. The source is sending a fiber state. But now we would like to have a strategy that is classical for the faraway Bob. So what do we do? Well, what we do is that if the switch actually routes the quantum particle to the long path, well, then immediately after the switch, we assume that this particle is being measured in the sigma Z direction, and a classical outcome B is obtained, +1 or -1. And this classical outcome now is sent by purely classical means to the faraway device, which simply outputs the value of B independently of which measurement is selected by Bob. Okay, so there is actually no quantum signal reaching the faraway device Bob. You know, if all this short path part of the experiment is done on a table, and if Bob is 100 kilometers away, so in my new strategy, everything is still done on a table, but then there is only classical data sent over 100 kilometers and no quantum particle. So if we follow this strategy, what will be the long path usage value? Well, if I look at the A1B1 correlator, so let's say A1 is the first measurement by Alice, so it's sigma Z. So remember the Bob side, whatever measurement I do, 1 or 2, the outcome Bob outputs is always the result of a sigma Z measurement. So what I get that the correlator A1B1 is simply the average value of sigma Z tensor sigma Z on the fiber state, which is 1. Similarly, A1B2 is 1. And now if I look at A2B1, A2B2, well, again, on Bob's side, it's always the outcome of sigma Z measurement, but on Alice's side, it's a sigma X, and the expectation value of sigma X tensor sigma Z on the fiber state is 0. And the CHS value is what? Is this plus this plus this minus this. So it's 1 plus 1 minus 0 plus 0 minus 0. So it's 2. So I have here a simple strategy where I observe maximal violation on a short path and a value reaching the classical bound. Okay, in contradiction with this claim that you can visualize here, that if the CHSA, the short path CHSA value is close to 2 square root of 2, the classical bound for the long path should go down. Here it doesn't go down, it stays the same, 2. Okay, and this strategy I introduce doesn't involve any long-range quantum resource. There is no entanglement established between Alice and the faraway device. There is no fresh randomness that is generated after the input is selected here. And of course, this kind of correlations, they cannot be used, let's say, for QKD, because this intermediate measurement here could actually be done by an eavesdropper, which would then have a copy of the outcome of Bob, so know everything that Bob knows, right? Okay. So what is the conclusion? The conclusion is that the kind of models of this kind that were considered by CVP to compute, to derive this trade-off, they are not general enough, okay? If I assume that the Faraway device behaves classically, assuming that the classical parameter that determine this behavior have to be set since the beginning at the source is too restrictive. These classical parameters, they can be obtained by measuring the quantum register B if it's actually rooted in the long path. Okay, and so even if I observe a high violation here in the short path, and I conclude that rho AB is a fiber state, and so uncorrelated to everything, I can still get A and the Faraway device share some correlations because this classical variable here, lambda, could actually be the result of a measurement performed on B, which is correlated to A. Okay, so this kind of analysis is too restrictive, and so we cannot apply this trade-off. Okay, so this led us to ask the question: what is a proper way to formalize what it means in such rooted experiment to have short-range quantum correlations or long-range quantum correlations? How can we certify long-range quantum correlations? Okay, so this is what I'm going to explain now, and this is something that we did in this paper. So we have the arXiv reference. Okay, so let's first, as you were saying, let's first just understand how we can mathematically describe this experiment without, putting any kind of restriction on what the Faraday device Bob can do. Okay, so a fully general quantum model for this rooted Bell experiment. So, as I said, we want to describe this joint probabilities, joint probability to get outcome A and B given input X, Z, and Y. So, in a quantum model, this will be given by straightforward application of the Born rule. So we have a state, ray B, produced by the source, and then the quantum particle produced by the source. They will travel through some channels. On Alice side, we could incorporate, if we wanted, the action of the channel, but you know, we can directly take that into account in the state produced by the source, actually. On Bob's side, however, the thing is different because now there are two possible channels, right? One channel if the short path is selected, and one channel if the long path is selected, and the action can be different in both paths. So we cannot, you know, include the action of the channel in the definition of the state produced by the source. So we need explicitly here to introduce a channel CZ that describe what happened in one path or the other. Okay, so then we have, of course, measurement operators that describe what's happening on Alice's side, and then measurement operators that describe what's happening in the two devices of Bob. And so this measurement operator will depend on the specific measurement Y selected, but also on the value of the switch, okay? Because these two boxes need not be the same. So the short path box may be different than the long path, right? So we have some Z dependency here also. This is one view. Equivalently, you know, we can view everything that happens on the left-hand side as just one big measurement device that takes two inputs, Y and Z, and produce one output. Okay, so this is closer to a standard description of a Bell experiment. And so we can write the joint probabilities as in a standard Bell experiment with some measurement operator here M prime, which, and what is the link between these two descriptions? Well, this CPTP map here describing the channels, the act on the state, but we can also take the adjoint, which will act on the measurements, and this will then define some new effective POVMs, which characterize the combined effect of the measurement device and the channel, right? So we can choose whatever description we prefer. Okay, so this is a general quantum description, but now we want to introduce a restriction, and this restriction is that somehow, you know, we are only considering short-range quantum correlation. So there is no like quantum data reaching this Faraday device, and we want to consider this restriction because we want maybe, you know, to prove that the data in an experiment is not compatible with these restricted models. Then we will have certified that some quantum information has to travel to the Faraday device. Okay, so we are led to introduce short-range quantum correlations. And one very natural way to do so is to say that short-range quantum correlations are the one that you can write in this way, but where the channel describing the propagation of the particle on the long path, this channel is entanglement breaking. So it cannot distribute entanglement, right? If we look at the perspective on the right-hand side, so if you look what happens if you have some untrusted measurement and you take the adjoint of an entanglement breaking channel, you can show that the effective POVMs will be jointly measurable. Okay, so this is shown in this nice paper by BilQC. Saying that this channel is entanglement breaking is the same as saying that the measurements, the long path measurements, so when I put Z equal to L, are jointly measurable. What does it mean for a set of measurements to be jointly measurable? Well, it means that instead of doing this, let's say I have n measurements here. If these n measurements are jointly measurable, it means that I can replace them by a single measurement that now return a string of outcomes, B1, B2, Bn, where the outcome B1 is the outcome I would get if I had selected here measurement 1. B2 is the outcome I would have gotten if I had selected measurement 2, and so on. So instead of doing these n different measurements, if they're jointly measurable, I can just do one big measurement, get a string of outcomes, classical outcomes, send these classical outcomes through a purely classical channel to the faraway device, and then when the input y is given to the device just look, what's the outcome I should put in the string, and output that, right? And of course, operationally, this makes a lot of sense and clearly characterize this idea of short-range quantum correlation that do not involve the sending of quantum information to the faraway device. Okay, so the most general thing you can do, if you have some source that produce some quantum system, and if you don't want quantum information to go beyond some point, is to do some measurements, that will map that quantum system to some classical systems. And so this is what this idea of joint measurement capture. Okay. Okay, but so now this is quite nice because it means that the short-range quantum correlations in rooted Bell experiments, they're the same as the correlation in a standard Bell experiment involving A and the measurements on this short path Bob device, but were added an additional measurement with more outcomes. Okay. And since we can characterize the correlation, the quantum correlation in standard Bell experiment with these non-cumulative polynomial optimization techniques, this maybe these SDP hierarchies that I guess you have heard of, that we can do the same here. Okay, so we can characterize short-range quantum correlation through these non-cumulative polynomial optimization hierarchies. And so if you give me some correlation characterizing a rooted Bell experiment, I can now decide if they are compatible with a short-range quantum model or not. Okay, if they are not, then we have certified that we have established long-range quantum correlation. So some quantum information had to be sent to the faraway device. It's not possible to reproduce the correlation without quantum information reaching the faraway device. Okay, so now that we have this tool, we can ask the question, do we get an advantage by considering this rooted Bell experiment? Are they better than standard Bell experiment? If we just focus on CHSH inequalities, we know that there is no advantage, okay? Because it's explicitly shown that there are models where you can have whatever the violation you observe in the short range, you can get a value of 2 in the long path, which is the same as the standard bound in a standard bell experiment, right? So there is no point in adding this measurement device here. You get the same bound, same classical bound in a standard and rooted bell experiment. Okay, but perhaps there are other inequalities that are useful, and indeed there are other inequalities. And one example is what I call this like BB84 witness. Okay, so let's assume that you do first. Let's look at a standard bell experiment where you assume the source produce a fiber state, and Alice and Bob both do sigma z and sigma x measurements, right? And then you can look at the correlation. How strong are correlated Alice and Bob if they both measure, sigma z, or if they both measure sigma x? And in this ideal situation, they're fully correlated in both cases, right? So this BB84 value here, we reach a value of 2. Okay, so you can reach 2 quantum mechanically, but in a standard bell experiment, you can also reach 2 with purely classical model. This is not complicated, right? You just send some classically correlated random variables, and you can also get that both one measurements are fully correlated, both the second measurements are fully correlated. So you cannot witness non-locality with this BB84 quantity. However, what happens if you add this short path additional measurement? And let's assume that the additional measurement you do are the sigma z plus or minus sigma x measurement, which allows you to witness a maximal CHSH violation in the middle, right? Then we get that the BB84 bound is not 2 anymore, but is something smaller, which depends on the CHSH value. And when the CHSH value is 2 square root of 2, this bound of 2 for the expectation value of BB84, now it goes down to square root of 2, which is 1.414. Why is it so? Well, if I observe a maximal CHSH violation in the middle, then I know basically there is a single strategy that can do that, which is I know that the source has to send a fiber state and Alice has to do this sigma z and sigma x measurement, right? So now if I want to look at what is the maximal value of BB84, if I assume that Bob is classical, I must introduce this this measurement just after the switch when the particle is sent in the long path. And this measurement has somehow to maximize this, okay? So it has to maximize this quantity where, on Alice's side, once in a while I measure Z, and the rest of the time I measure X. And then a single measurement that can maximize this correlation would be a measurement that is intermediate between X and Z. And so if you do such a measurement, the maximal value that you can get for this BB84 expression is then square root of 2. Okay. So if I observe something above square root of 2, then it means I've certified that some quantum particle had to travel to the faraway device because I cannot reproduce this value of 2 by doing a measurement before this faraway device. Okay, so there is actually an advantage of using a rooted bell experiment, right? You can some bell expression like BB84, which have a classical bound in a standard bell experiment, will have a lower bound in a rooted bell experiment when you condition on the observation of some violation here in the short path. Okay, but now how is that useful for the problem of photon losses? So we look at some specific case. So we look at an ideal situation again, where you have the phi plus state produced in the middle, Alice the sigma z measurement. The short path Bob does this x plus minus z measurement. So ideally we get 2 square root of 2 in the middle. But now we will take into account the fact that we have losses. So this CHSH value will go down. And then for the Faraway device, we looked at 2 cases. Either the x plus minus z measurement are done, or the xz measurement are done. And also we get some losses. And then we can ask, given some value of the short path detection efficiency, what is the minimal long path detection efficiency that is necessary so that the correlations are not short-range quantum? And we can answer that question with our SDP tools based on non-competitive polynomial optimization. Okay, and so this red line, this is what you get in a standard Bell experiment. Okay, so if I forget that there is this Bob in the middle here, I fix the efficiency of Alice, eta s, to some value. I look what is the minimal efficiency of beta of BL to violate the inequality. I get this red curve. But now if I add this measurement in the middle, then I see that at least if the efficiency of Alice is high enough, I can reduce the minimal efficiency that is required. And here I have 2 bounds depending on whether I do this x plus minus z measurement, this is the black curve, or I do this xz measurement, this is the blue curve. Okay, and you see that in the case where I have perfect efficiency in the short path, so 1, in a standard Bell experiment, I would need an efficiency for the distant Bob of at least 70%, but now this can go down to 50%. Okay. As before, the region where we can establish long-range quantum correlation is this red region in parameter space. This black curve here, this is what they claim this paper by CVP you could get, but as you have seen, this was based on some too restrictive model. The other black curve, this is what you get in a standard Bell experiment. So we see that we get an improvement over a standard Bell experiment, but it's not as strong as was expected by CVP. Okay, we cannot have, if we fix the efficiencies of the device close to 1, we cannot tolerate arbitrary low efficiencies for the Faraway device, but we can improve over a standard Bell experiment. Okay, so this is already nice. In some other paper, so here we have the reference, we use this result in the context of device-independent quantum key distribution. So we assume that we have Alice in our lab, Bob in our lab. In the middle, we have the source. We have also the switch, these additional measurements. And, in some round of the protocols, Alice and Bob will just check the short path, let's say CHSH value. In some other round of the protocol, they will look at the correlation in long path. In some yet other round of the protocol, they will do measurement to get a key. Then, people have developed tools to compute the key rate you can get in the DIQKD experiment based on standard Bell test. So it was not too difficult to modify this tool to make them work in the rooted Bell setting. And so we're able to compute key rates. So again, we assume that we have some efficiency for a device close to the source, some efficiency for the device far away from the source. We also assume some visibility mu for the experiment. And then, we can fix all these parameters, plot the key rate, and, the solid lines, this is what you get in a rooted Bell experiment, and the dotted line, this is what you get in a standard Bell experiment. And you see that we improve the situation. Okay, so we can get positive key rates with efficiency for the faraway device, which are much lower than in a standard experiment. Although this advantage really depends on the fact that we have very good bell test in the short path. Okay, when the efficiency in the short path goes below 96%, then we don't see anymore a big difference. Okay, but there is some advantage. Okay, so now if I go back to this picture, so you know the motivation of CVP for introducing this routable experiment was that we could, I mean, they believed that they could get arbitrary small detection efficiency for the remote device of Bob and still witness genuine quantum correlation. In the examples we have looked at, we see this is not the case. But maybe, you know, there are other kind of experiment we didn't think about, other states or measurements you can use in a routable experiment that would allow you to go down. So is this possible? So to study this, first we realized that there are actually some limitation on routable experiments which are very general. So basically consider a routable experiment where you have n measurement device for the faraway device Bob. Then it's not difficult to show that there will always be, so if you have losses, okay, there will always be a short-range quantum model if the efficiency of the faraway device is below 1/m, okay, if I have a measurement device. So for instance, if we have the choice between two measurements for the faraway device B, then we need the efficiency of the device to be above 1/2 to witness long-range quantum correlation. We will never be able to go down. Okay, so 1/2, by the way, this is what we got here. So this kind of CHSH or BBT4 examples, we found that they are actually optimal in that sense. So why is this bound of 1/m? I mean, it's quite easy, okay? So what we need to show is that there exists a joint measurement we can do here in the middle that will reproduce our quantum experiment when we have n measurement device. And the way we can do that is simply, you know, what this joint measurement can do is simply guess which measurement will be performed here. Okay, so there are n possible measurements. You will guess, let's say, it will be the third measurement that will be done. And then that measurement device does that third measurement and send the outcome to the faraway device. What does the faraway device do? If the input is 3, the third one, as guessed by the measurement here, it gives that outcome. Okay. If the input is another one, it will simply output no click. I don't commit myself. I pretend the photon was lost. Okay, and this will, of course, reproduce the quantum correlation, provided the efficiency is smaller than 1/m, because the fact that this measurement here close to the source guess the right input for the faraway device, this happens with probability 1/m. Okay, so it's 1/m of the times that you actually produce a click. Okay, so we have so this is a simple strategy that shows you that if you want to find experiments that tolerate arbitrary low efficiencies for the faraway device, you need to consider experiment with many measurement settings. So actually, you can improve these bounds. So I will not go into details, but basically the general question you can ask is, given that I have m measurements which are done with some efficiency, when does there exist a joint measurement that reproduce that? And in some other paper, the reference is here, we studied this question, and there are many kind of different bounds we derive. So here is one example. So I don't explain it in detail, but you see that there is a relation involving the number of measurement performed on Bob's side, on Ali's side, the efficiency on Ali's side, efficiency of Bob's side, the visibility also of the measurements, and whenever the relation between all these parameters satisfies some inequality, you can always prove that there is a joint measurement. If you furthermore assume that the device measure system of a given dimension, you can also improve these bounds. But okay, so this puts restrictions on what you can expect in routable experiment. But the message basically is that if you want to go to large distance, tolerate low detection efficiency, you need to consider experiment with more measurement settings here. Okay, so if we do that, can we then reach that bound? Okay, is it actually possible? Okay, so this is what we look in this paper, which we put on the arXiv 2-3 months ago. And we show this is indeed possible. So this efficiency of 1/m can be reached. And we show this can be reached by doing a connection with steering. So what is this connection? So again, to make things easier, let's assume that in the short path, you do a perfect, an ideal CHSH experiment. Okay, so you measure phi plus state with sigma z, sigma x measurement for Alice, z plus or minus x for the device of Bob close to the source. So you get a violation of 2 square root of 2. Then even if you were not actually trusting what Alice's device was doing, just by the fact that you observe a violation of 2 square root of 2, you know that up to local imageries, Alice's device has to implement sigma z and sigma x measurements. And of course, now if you look at the long path experiment, because what Alice does should be independent of what happens on the right, you know that also in the long path, Alice has to do the sigma z and sigma x measurement. And so this means that what you're looking actually in the long path is not anymore a bad experiment, but it's a steering experiment. Okay, so the steering experiment are, if you want, one-sided device-independent experiments where you trust one side, here Alice, and you don't trust the other one. Okay, so this is the first thing. The second thing is that if I look at the correlation in the long path, I can write them using the Ball rule in this way. So it's a trace of what? The measurement operator on Alice side times some state, but this state now is the reduced state obtained from rho AB when I have done the measurement on the faraway Bob. Okay, so when Bob does a measurement on his device, is actually remotely preparing some state for Alice. And I call this state rho B given Y because it depends on both on the measurement it does and on the outcome. So in the context of steering, this is called an assemblage. And now if I look at the condition for this long path correlation to be short range quantum, it means that I can write them in this way, where what is rho lambda? Rho lambda is the reduced state obtained if I perform this joint measurement here just after the switch, and I get some classical outcome lambda. And then I have the priority to get outcome B if I choose input Y, and I have the classical value lambda on Bob's side. But if I equate these two things, I see they are the same if the assemblage on here can be written in this way, and this in the context of steering is what we call a local hidden state model, which can be ruled out if you violate a steering inequality. So in summary, we have this connection with steering that tells us that if the long path correlation violates a steering inequality, then there are not short range quantum correlation and they are generally quantum. Okay, so now the question is, if I assume Alice is doing some sigma z, sigma x measurement, are there steering inequality which can be violated even if the efficiency on Bob's side is arbitrarily low? And yes, they are. They were introduced in this paper by Paul Skripczyk and Daniel Cavalcanti. So they are quantum correlation involving trusted sigma Z sigma X measurement on Alice side and n untrusted qubit measurement for Bob that are steerable if the efficiency, is 1/n. Okay, and this saturates the previous bound I had shown before. So ideally, if we have a CHSH, perfect CHSH violation in the middle, this is possible. What if we don't have a perfect CHSH violation? Then we can no longer use directly this connection to steering, because then we cannot guarantee that Alice is doing exactly the sigma Z and sigma X measurement, and everything become much more tedious. But in this paper, we do this analysis. So I will not enter into the detail, but basically we introduce this. So this is a short path CHSH violation. Then on the long path, we introduce two bad expectations, and then we derive a nonlinear relation that relates these three quantities. If you assume that you have short-range quantum correlations, and basically, I mean, this W play the role of a long path band inequality, and the bound that you get will depend on the amount of CHSH violation in the short path, and also on this Tn quantity, which basically measure the average detection efficiency on both sides. So I don't get into the detail, but if you apply this kind of analysis basically to an experiment where you have a violation in the short path of 2 square root of 2 minus epsilon for CHSH, you will find that in long path, you will get a proper, band violation if the efficiency is basically 1/n times some factor that depends on epsilon. So it's actually a little bit higher than 1/n, but as epsilon goes to 0, this approaches 1/n, where n is the number of measurements. And so this saturates this bound I had shown before. Okay, and so if you increase n, so if you increase this number of measurement setting on faraway device Bob, you can tolerate efficiencies that are as low as you want. And so in principle, you can, in a device-independent way, establish genuine quantum correlation at arbitrary distances. And what is nice in this rooted Bell experiment is that you can do this only with qubits. And in a standard Bell experiment, this is not possible. So you can prove that any standard Bell experiment that that involve measuring qubit on Alice side and qubit on Bob side, no matter how many measurements you do or what are these measurements, this experiment will always admit a classical explanation if the efficiency is above, say, 1/2. I think it's 2/3 maybe, but let's say at least above 1/2. Okay, so there are Bell experiments that people have shown are actually robust to arbitrary low detection efficiencies, but they require a high dimensional quantum system, and the dimension of the quantum system you need to measure. They increase as you lower the detection efficiency. Here, by using this rooted Bell experiment, we can go to arbitrary low efficiencies, only measuring qubits. Okay, so basically this is what I wanted to tell you. So now, where do we go from here? So now that we have this genuine quantum correlation, which we can certify our arbitrary long distances, we can ask if we can actually build long distance device and DIQKD protocol out of them. And this is something that we are looking. It's not straightforward because even in a standard scenario, if you have non-local correlations, this doesn't imply that from these non-local correlation you can have a device and DIQKD protocol that is secure, because establishing a key is a bit more demanding than just observing non-locality. So you need the violation to be high enough. Okay, so this is something that we are currently looking, but at least in the case where everything is ideal, you assume there is no noise. In principle, yes, you would have a DIQKD experiment that is robust over a very large distance. But of course, we want to be realistic and consider a situation where you have noise, where the violation in the short path is not perfect, and this complicates the analysis. So this is something we are looking. Another thing you could ask is I consider rooted experiment with a switch only on one side of the source. You could put maybe a switch on both sides of the source. So my student, Edwin Lobo, which actually is the one which is has worked a lot on all our results on this rooted experiment. So this is something that he has been looking recently, and we do find some improvements if you have switch on both sides. Another thing you could consider is that, so far I always assumed in my analysis the validity of quantum theory. But you could ask, what kind of conclusion can we draw from rooted Bell experiments if we assume that the experiment is not described by quantum theory, but let's say by some possibly supra-quantum theory, but compatible with the Noething principle? So this is also something that we are currently looking at the moment, but I don't have yet any result on that. So in conclusion, I think this idea of rooted experiment, which was introduced by Pawlowski and his collaborators, is actually quite nice and improved the prospect for certifying long-distance quantum non-locality. But this improvement that we see, they require some very good short-range non-locality tests, which are in principle doable, but still highly demanding. And there are still many. I mean, this is a subject that has been not so much explored so far. So maybe there are some new findings to be expected. Okay, so I think I will stop here, and I thank you for the attention.